Welcome to Lesson 7b, Evaporation Thermodynamics, Category 1. We're going to talk about some of the thermodynamics of evaporation. I will talk about something called Category 1 evaporation and do an example. We'll deal with Category 2 on the next lecture. What is Category 1 evaporation? It's when you have a liquid and you're in conditions where the room, we say room, this could also be the ambient. It doesn't have to be a room, it could be a tank or something. We're talking about a sealed container generally, or one that's almost sealed, and the ambient or the room temperature is less than the critical temperature, and the pressure of the room is less than the critical pressure. You remember from thermodynamics, a TS diagram. When you're talking about water, we call this blue curve a steam dome, but it turns out that you have a similar diagram for other types of substances other than water. And so just to refresh your memory, this blue line on the left would be the saturated liquid line. They call it a line, it's actually a curve. This is the critical point, and we have the saturated vapor line on this other side, on the right side, and anything in between would be a mixture of liquid and vapor. So it's liquid plus vapor inside the dome. We call this the dome. Everything to the left and under the critical is called a liquid. Everything to the right and to the right of the critical line, this purple line, is a gas or a vapor. Everything above the critical point, this is called a supercritical fluid. It's not really a liquid or a gas, it's a supercritical fluid. So this is a gas, or in air pollution we call it a vapor, not a gas. These other curves are isobars that I have in black, but there's one special one, and that is at some particular pressure, it's the pressure of the room. This purple one is the pressure when it's PC, critical pressure. Temperature is on the vertical scale, so there's also a temperature of the room temperature. We can pick one of these. We'll pick the one that intersects T room. So this point right here would be PV of the substance that we're talking about. This is a pure substance here. So pressure is PV at T room. That's the vapor pressure of the substance. And so this particular isobar would be P equal PV. One of these isobars is P room, one of them PV. We see here that PV is less than P room in this particular case. I should mention that this is the TS diagram for a pure substance. Now in our problems, the key is going to be this. The above is for a pure substance, one chemical. If you have a mixture of chemicals, and what we'll be talking about mostly is some VOC in air, this diagram is still valid. Everything's valid except these pressures must be partial pressures, Pj, instead of total pressure, P. And then Pj has to be less than P room, otherwise it doesn't make any sense. So you have some air plus species J, and species J can be either a liquid and a vapor, or all vapor or all liquid. And we're going to look at cases where we're talking about evaporation of liquid species J into air. And so Pj will always be less than P room because you always have some air in there. Appendix A10 in our book has a bunch of chemicals and their critical temperature and their critical pressure in atmospheres. So if this is above 1, that means PC is greater than typical room pressure, which is atmospheric pressure of 1 atmosphere. So for all these cases, we see that PC is greater than P atmosphere, 1 atmosphere at SATP conditions. And so that's part of our category 1. PC is greater than P room. So we see that all these chemicals satisfy that part. All these would lend themselves to being category 1. The temperature, on the other hand, notice that TC is sometimes, like here, these are actually negative. TC is sometimes less than T equal 25 degrees C. But for most of these cases, TC should be greater than T room. So if we're talking about ambient SATP, most of these substances would be a category 1. We're going to do the same thing we did with these isothermal conditions where we do experiments for equilibrium isotherms. This is a thought experiment here. Imagine we have a container with a frictionless piston, and we have some pressure up here, P atmosphere, and then we have some liquid, VOC, in here that starts to evaporate, and this is initially air. So it'll be air plus species J as it evaporates. And this frictionless piston can go up and down as needed to keep the pressure constant. And then we also have some heat, Q dot, coming in or out, either adding or removing heat. And we will do this such that we maintain T equal constant. So here's our temperature of the liquid and the gas. That remains constant at all times. So let's suppose that there's some kind of a membrane over top of this at T equals 0, and at T equals 0 we remove the membrane, so suddenly that liquid is exposed to the gas and it starts evaporating. Let's just write it this way: at T equals 0, all air, no vapors of J. And at T equals 0 plus, meaning at microseconds after 0, we remove the membrane and we start the evaporation process. So evaporation begins. And then, as I said, Q dot is added or removed as necessary to keep T equal constant. So this is an isothermal process. What do we expect to happen when we start at T equals 0? We expect a behavior that looks something like this, and it will not reach 1 because you're never going to get Yj equal 1 because you always have some air in there. So instead, we're going to exponentially approach some constant Yj steady state. And we'll call this the final state, and we'll call this the initial state or the 0 state. At this final state, the air is saturated with J vapors. And you can't get any more than that. If you tried to put more vapors, they would condense along the walls and go back into the liquid. We can calculate this YJSS. Yj steady state is equal to PVJ over P, because it'll reach the vapor pressure of species J. This is the upper limit for Yj, and there's a big assumption made here. You'll get this if you have enough liquid to saturate the air. So as I drew it, I have a lot of liquid in there. But suppose you start this process with a small amount of liquid, and you do the same experiment. This will start evaporating until all the liquid's gone. So you have to have enough, and I'm going to show you how to calculate that. But I just wanted to say that you could also draw this same sketch in terms of partial pressure Pj, and there would be a PVJ, and the curve would approach PVJ, again assuming that we have enough liquid to reach that upper limit. Pj would reach PVJ. That's the max or the F final condition. This is the 0 condition, same as the previous diagram. If not emaugh liquid to reach the steady state conditions or PVJ, what happens? Well, in that case, Yj max is simply the number of moles of liquid that you start with over the total number of moles in the system. And so Yj max would be less than Yj steady state in this case. If you have a small amount of liquid and it all evaporates, you're going along exactly the same curve you have here, except you reach a point where you have this maximum at which all the liquid has evaporated and there is no more, so that's where you're going to stop. So your final condition would be there. And the same thing happens on the PJ diagram. There would be a PJ max, which is less than PVJ because all the liquid is gone. And then nothing happens from then on. So in solving these problems, you have to look at how much liquid you have compared to how much air you have. Use this equation to figure out if you're going to evaporate all your liquid or not. How does the evaporation process look on our TS diagram? Again, the red one is P equal P room. We have T room down here, and we have this one is P equal PV. I'll put it J now. This is PVJ. Remember, our process is isothermal, so we must follow a horizontal line in our process because T is on the vertical axis. So if we are at T room, we're stuck on this line no matter what happens. So just think about this process. We start with Pj equal to 0, and then we start increasing. P is increasing to the upper left, so P room is bigger than PVJ in this case, for example, and P room is less than PC, so pressure is increasing that way. So if you think about what's going on with the substance J, we start somewhere here where Pj equals 0, no vapor, it's all liquid. So Pj is equal to 0, and now it starts evaporating. So PJ is going to increase because now we get some vapors in the air. PJ is up. So this is evaporation process happening. So some of that liquid is evaporating, so PJ keeps going up, and it'll keep going up until one of two things happens. Either it'll go all the way to PVJ, and then it'll stop evaporating. So this will be our F condition. Finally reaches PVJ, and then it stops evaporation from there on. Or you can stop at some other location where PJ is less than PVJ, but bigger than 0, obviously. You have some vapor in the air where all the liquid is gone. In order for this case to be attained, you must have enough liquid initially, or you're never going to get there. And so this second case here is when all the liquid is gone, not enough liquid initially to reach PVJ. It all evaporates, and then you have no more liquid to evaporate. So just a few notes. The upper limit of PJ is PVJ. We're never going to get higher than that. You can't, because it would start condensing and go back to PVJ. So you can't have more PJ than PVJ, just like relative humidity can't be more than 100. By the way, this works for water too. You can do this to solve relative humidity problems as well for water, but we're typically talking about chemicals. State 0 is pure air, so PJ equals 0. State F is one of two choices. Either it's saturated, PJ equal PVJ, and that's if enough liquid is there initially, or it's not saturated, so PJ is less than PVJ if not enough liquid. You have to know which one this is. You have to look at how much liquid is in there in the beginning. This will be clear with an example. 0.550 kilogram of liquid methanol enters the bottom of a closed tank of volume 3.8 cubic meters. Initially, the air is pure, but the methanol suddenly begins to evaporate as soon as you put it in there. Temperature and pressure in the tank are given, and we want to do 4 things here. We're going to determine the category. This one's going to be category 1 because I haven't taught you about category 2 yet. That's for next time. Calculate the number of kilomoles of air or methanol in the container, and then determine whether some or all of the methanol will evaporate. That's the key before we can get an answer. Calculate the final mole fraction, and then I just asked to kind of review previous stuff. Will it explode if there is a spark? First of all, assumptions and approximations, and you'll always make this approximation unless I tell you otherwise. We'll assume that V of the liquid is much, much less than V of the air. So we're talking about a case where we have some container and the liquid is just a small fraction of the volume. So we'll let V equal constant at all times. We'll ignore any displacement effect. In real life, as this liquid is removed, it's evaporated. The volume in the tank, the gas volume, becomes larger, but we're going to assume that volume is constant. Otherwise, this gets much more complicated. A, is it category 1 or 2? Well, from table A10, for this particular chemical methanol, we see that PC is 78.5 atmospheres, which is much greater than P of the room, which is only less than 1 standard atmosphere. And TC is 240 degrees C, which is much greater than T room, which is 21.2 degrees C. So those are the 2 criteria to call this category 1. For the air, let's use the ideal gas law, PV equal nRUT, to calculate an air, PV over RUT. So let's just plug in the numbers, watch your units, 99.5 kPa times 3.80 meter cubed over universal gas constant, 8.314 kilojoule per kilomole K. And then T I converted to K, don't make that mistake. And then some unit conversions, kilojoule per kilonewton meter. A kilonewton per meter squared is a kPa. All the units cancel except kilomole on the bottom of the bottom, which means it goes to the top. So N air equals 0.1545 kilomole. For the methanol, Nm is the mass of the methanol over molecular weight of the methanol. Look up the molecular weight. I typically use the NIOSH Pocket Guide online because that's convenient to do. 32.1 kilogram per kilomole we get N of the methanol. Number of moles of methanol is 0.01713 kilomoles. These number of moles are fixed. They cannot change unless you have some kind of chemical reaction going on. But we have nothing like that here. So in other words, we have a certain mass of methanol, we have a certain mass of air, so we have a certain number of kilomoles of air and methanol, and those cannot change. It's in a sealed tank. It's the same number of moles regardless of whether it's liquid or vapor. It's all liquid at T equals 0, and then it goes to either all vapor or some vapor, depending on whether it's going to have enough liquid to do that or not. What's happening is the evaporation changes the methanol from liquid to vapor, but NM remains constant everywhere. It can't change. Determine whether some or all of the methanol will evaporate. The best way to do that is to use that equation I gave you. So if it all evaporates, Ym max, the mole fraction of the methanol, maximum possible, is N methanol over N air plus Nm. That's just coming from this equation that I had given you up here. This is the maximum possible if all the liquid evaporates. And that would be this case if we don't have enough liquid. We can quickly calculate that because we just calculated Nm and air. So you plug those values in. The units on top and bottom cancel, and this becomes 0.09983. Keep that in mind. This is the maximum possible mole fraction. All the liquid evaporates. Now the question is, does it all evaporate? Well, the next procedure here is to compare to the mole fraction at saturation conditions. If we keep going all the way to the steady state conditions, if we go all the way to here, we'll have Pj equal Pvj. If we don't have enough liquid, remember we go to this case. So I basically calculated this case now, and now I want to calculate this case and see whether we have enough liquid to do that or not.
How do we calculate that?
We go to Appendix 8.8, and at the given temperature, T equal 21.2 degrees C, you have to interpolate. We get PVJ is equal to 100 millimeters of mercury. That's actually one of the numbers right on the table, so we didn't have to interpolate. So Ym saturated would be when Pj is PVJ divided by total pressure. Remember, Yj is Pj over P that we learned the first week of class, 100 millimeters of mercury over 99.5 kPa. Here's the importance of writing your units, because we have to get these units to cancel to get a non-dimensional, non-unit Y. So 101.325 kPa per 760 millimeters of mercury is 2 units for the standard atmosphere. And this turns out to be 0.1340. So Ym max possible equal Ym sat equal 0.1340. But here, our max Ym is when all the liquid evaporates. That's what I had calculated up here. So we had Ym max for our case was 0.09983. So since 0.09983 is less than 0.1340, we would say that all of the liquid evaporates. If we had enough liquid, we could eventually reach this. But since we don't have enough liquid, we know that it's going to stop evaporating when all the liquid evaporates, and we're only going to get up to here. We can't get any higher because we ran out of liquid. So that's the answer to part C. And then finally, part D is to calculate the final mole fraction. Well, it's going to be either one of these two, either this one or this one, because that's the two possibilities. It'll be the smaller of the two. In this case, all the liquid has evaporated, so the mole fraction is equal to 99,800 ppm. And then finally, we want to see if this thing was explosive, so I look up LEL is 6%, convert that to ppm to compare. 60,000 ppm, lower explosion limit, upper explosion limit is 36%, is 360,000 ppm. Our Y is in between, so I would say yes, it can explode. Might not explode, but it can if there's a spark, and so that's the answer to that. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.